Hi everyone, thanks for having me. I am Bruno from here, Brazil. I am head of engineer at Vintium. I work on Bitcoin Core, fuzzing, mutation testing, and other projects. And today I'm going to talk about when fuzzing meets mutation testing. First of all, I know you had some talks about fuzzing here, so I won't spend a lot of time explaining it. So let's start by introducing mutation testing. Well, if you work on a Bitcoin project, or better, if you work on any other software project, you probably write unit tests or functional tests, whatever. However, automated tests are softer, right? So how do you know your tests are correct? Usually, I know that most people rely on, for example, code coverage reports, but I think they don't say too much about the quality of your tests, right? So that's why mutation tests exist, basically. So mutation testing is a technique that evaluates the effectiveness of a test suite by introducing small changes that we call mutants into the code and checking whether the tests detect the resultant behavior difference. And I have an example here. So this is a clear example. You can see that we mutated that code by changing A equal to B to A different to B. So this is a change. And this is example. This mutation was not called by any automated tests. So this is mutation test. It's basically you change something in your code and you see if your tests can detect it. Okay. This is used by many big companies like Google. They use it, Facebook, and other big projects. I think some Bitcoin projects also uses mutation testing. Like I know Bitcoin Core, of course, but I know Rust Bitcoin and other ones. And okay, so I'm talking about mutation tests and fuzzing. So what is fuzzing? I said that I won't talk too much about it because I know you had other talks. But basically fuzzing, I could say that fuzzing is an automated testing technique that feeds a program with large amounts of randomly or semi-randomly generated inputs to uncover crashes, vulnerability, and unexpected behavior. Probably you see many memory bugs, and yeah. But CD corpus, since fuzzing is a search-based technique, having an initial set of inputs to help the processes is very important. So this is why we have the concept of CD corpus, and some open source projects like Bitcoin Core maintain public CD corpus, so you don't need to fuzz from zero. If you want to run like Bitcoin Core fuzz testing, you can go to the QA assets repo, download the corpora, and you can run from that inputs, okay? So it's important to know what is a CD corpus for the context of this talk. And, okay, yeah. In 2022, I guess, I don't remember exactly, I think so, Chaincode Labs got in contact with some researchers about Bitcoin Core's fuzzing efforts. And the result of this research is basically this paper, like looking for lacunae in Bitcoin Core's fuzzing effort. It was presented at the International Conference of Software Engineering that will be held in Brazil next year, by the way. Okay, but so they looked for lacunae and Bitcoin Core's fuzzing efforts because they wanted to investigate the saturation problem. And by reading this paper, I noticed they employed mutation testing to evaluate all the Bitcoin Core's testing efforts, especially for the TX verify file, because it's a critical one. So they employed mutation testing, and you can see that functional tests could get like 73% of the mutants, and there's a difference between what unit tests and functional tests can cut, and yeah. So here they used a tool called Universal Mutator. It generated like 430 compiler mutants for this file, and then they also run two fuzz targets. So process message TX and another one. And I was reading this paper, and there's something that really got my attention. So this paper is about like finding lacunae in Bitcoin Core's fuzz testing. And reading this paper again, there's something that really got my attention. And it was exactly this statement here, because they said like they noticed that fuzzing was able to detect only 12% of all mutants. So while functional tests and unit tests got like 73%, 80% of all mutants, they noticed that fuzzing could detect just under 12% of all the generated mutants. However, this is not really a bad result, because fuzzing basically detects like crash-inducing bugs, like memoritious, and you know, right? So it's impossible to cover all the possible cases in the harness. Of course, you won't put like a huge if else on our harness. So this is not a really bad result. It's expected. And they say like, this is one reason differential fuzzing is promised, because a first implementation, like Bitcoin Core, is such a specification. So they also point this. And okay, so I was reading this paper, and okay, they used mutation testing, and okay. So fuzzing could detect just under 12% of all generated mutants. Cool. This is not necessarily a bad result, I agree. But I was not convinced that fuzzing is really bad to kill mutants. Even it makes sense, of course, theoretically. So what I did, basically, based on this provocation, I worked on an empirical evaluation of fuzz targets using mutation tests. So I worked on this paper. So an empirical evaluation of fuzz targets using mutation testing. This is a peer-reviewed and published paper, by the way. So the idea, of course, is like verifying if the fuzz test could detect this number of mutants or could detect more. Like, let's see. So initially, I chose basically 10 different Bitcoin Core's fuzz targets that address different areas of the code base. I don't know why 10, sorry. And I don't know why I chose these 10, but yeah, I chose 10 different targets. And what I did is basically I applied this methodology. So basically, I ran the mutation analysis executing only the cases from Bitcoin Core CD corpus twice. The first run, I executed the targets as they are. So basically, I just executed them. But in the second run, I removed all the assertions from the targets. Okay, so I ran the mutation analysis basically twice. So with the assertions and without the assertions in the target. And okay, so here we have the results. When I got these numbers, I got scared. So, whoa. Many targets were able to kill over 70% of the mutants. And some of them reached 100%. This is a super good result, right? And also, we have the mutation score with the assertions and without the assertions. And we can see that without the assertions, the mutation score drops. So for example, we have, or we don't have, now we have 81% and then 63, 82%, but removing the asserts drops to 44%. Okay, the results are great, so this is cool. But what makes this target special? Like, why? Because in that research, they said that for the TX verify functions and the fuzz target, it could detect only 12% of the mutants. And we saw that this is expected because of the nature of the fuzz testing. But when I run mutation analysis for other targets, I saw that some of them reached 100% or 70% or 80%. And one thing that's important to say here is that I just run it using the cases from the CD corps. I could run it for longer, like for more minutes or hours, and I'm sure that it would detect even more mutants. But now comes the second part of this research. So why? What makes these targets special? What they have, like, because there are some targets that can detect like 12, 10%, but you have many targets that can detect 80, 90, or 100% of the mutants, more than the functional unit tests together. So what makes this target special? So I started investigating, and the first thing is round-trip functions. This is obvious. So if you can assert that a deserialization matches a serialization, a decode after an encode, of course that any mutant introduced in one of these functions, you make this relation to fail. So for example, we have many targets for serialization, deserialization stuff. If I introduce a bug, a mutant, on the serialization code, of course, when I try to do this round trip, it will fail, right? So this is one of the reasons. I know this because of the batch 32 round trip fuzz target. So here we have basically the encode function. Then we have the decode with the encoded one. And then we assert, like they are basically the same. So of course, if I introduce a mutant in this function or this one, of course, this assertion will fail. So it made the target to detect like many mutants. This is the reason. So, yeah. The second thing we notice is the strong oracles. So we notice that it's possible to determine correct output for arbitrary inputs depending on what you are testing. So one of the targets that reached exactly 100% of the mutation score is the fifrac div fallback. So rather than relying on an external specifications, this target basically implements I would say like a redundant reference calculation, use some alternative libraries. We can say that's basically differential testing. I don't know if I can say this, but yeah. So you are really testing the behavior against an alternative library. And of course, if I introduce a bug on one of these functions, it will like be called. So this is another example, I guess. Yeah, fifrac div fallback. But this is just one target. I think the third thing, and I think one of the most important one, is metamorphic relations. So what is metamorphic relation? What's a metamorphic relation? So metamorphic relation is when you can assert relationships between multiple inputs and their outputs. So I can show you a super dumb example. So okay, here we have a fuzz target, and we have a function called isOdd. Okay, so what I do here is basically I consume a number x, then I pass this number to I send this number to the function isOdd, Then I verify the result is basically true or false. Okay, this is basically a very simple fuzz target. So it's super simple, but okay, nothing wrong. But I think I can improve this target. Because if I introduce a bug on this function, like is odd, if I introduce if I create a mutant or introduce a mutation in this function, I don't think this target will caught anything, because it's just a simple target, you know. And I know that most of the targets are basically this way. But to give you an example about how we can put like metamorphic relations, we have basically this target. So I have the same number, and I have the first execution. Then I can, for example, get that number and +1 or -1, ensure that the second execution with that number, and then I can assert they are different, the results are different. So, of course, I can't put like a huge if-else. If the input is 1, do this. If else if this. If 3, if 4, if 5, if 6. Of course, we don't do this way. But I know that if a number is odd, this number +1 or -1, the result is different. Like it is not odd if that number is odd. So this is metamorphic relation basically. So this is an example. Yeah. So I know that most targets are basically this, but sometimes you can improve and have some metamorphic relations like this. And if I introduce a bug in this isOdd function, here we will detect that bug because we have the assertion, and we are basically verifying the behavior with 2 numbers, and yeah. Okay. So yeah, let me get back. So the results were great. So we have 2 targets reaching 100%, and we can see that this 182 is the batch 32 round trip. So round trip functions. We have this one that reached 100% because it's address manager, serialization, and unserialization. And other ones like BIP, the cipher round trip again, and the fifrac div fallback, right? The other ones, we got like 50%, 40%, 25%, which is expected. But for these specifically, we got a high number. So the conclusion is basically that the evidence that we presented in that paper, it suggests that depending on how we write the fuzz target, we can detect more bugs. So we have to pay attention on how we are writing our fuzz targets. If we can put metamorphic relations, please put. And also, if we can, for example, have differential fuzzing, it's also powerful to detect mutants. And yeah, the general conclusion is the way you write the fuzz targets matter, basically. So yeah, that's all. Thank you. So, questions?
Yeah, thank you. Check. Thank you for the great talk. This seems like super low-hanging fruit for like all projects, just to determine the to measure like the strength of the fuzz tests. Is this something that's easily adaptable to other repos, just to get metrics on fuzzing?
Yeah, I would say yes. We have a lot of mutation testing tools that you can use to generate the mutants, and then you can run your fuzz targets with these tools. So it's easy, like to run this same analysis for other projects, and yeah. For example, for Rust, we have the cargo mutants that's used by Rust Bitcoin project. So yeah.
That's cool. Thank you.
More questions?
Maybe you talked about it or I missed, but is the paper available? Like,
Yes.
Okay.
You can.
Just like Google it and PDF type.
Yeah.
Okay.
PDF is available. It's open. Yeah.
Thank you.
Okay. Thank you.
Thank you, Bruno. I think there is one more question there.
Bruno, thank you. I have one question because I'm not very familiar with mutation testing. Does it employs only mutation to controlling statements, or it can alter constants and math statements as well?
Yeah, it can do it as well. The tool I wrote, I think it has basically 25 different ways of mutating the code. So we saw a basic one, like changing the equal to not equal or not equal to equal. But you can, for example, delete function calls. There are many other ways of mutating the code, yeah.
How the situations are handled when the code doesn't compile after mutations, or doesn't run, or crashes instantly, or it works but simply in a completely weird way that not expected, but still passes the differential fuzzing?
Still passes what? Sorry?
Differential fuzzing tests.
So you mean that you have a mutant and then you run differential, you run your tests and fuzzing and it passes, you mean? Like?
Yeah, I mean like the software is working, but it's not doing its function correctly. So it looks as working for automated tools, but it would not be accepted by user.
Okay. It's not working for the user, like.
Yeah, maybe let me explain on some example.
Yeah.
It's mostly not about server-side software, but like in user software, user-facing, you may get some strange artifacts, but it still works and passes the test.
Yes. So maybe your tests are not good. So if it's passing your that behavior, like. Yeah.
Yeah, so mutation test is a way to test your test.
Yes,
if
exactly.
I understand it right.
Yes, exactly. Basically, you introduce bugs, and you see if your tests can detect that bugs.
Yeah, so
it's basically the idea of mutation.
The idea is one step from just coverage tests.
Yes, yes, because cover is like you're covering, but you can say like you are really testing that code, you know. So that's why mutation tests exist, because you can basically introduce bugs and see like, okay, my test can detect it or no, so I have to improve my tests, write more unit tests or functional tests or whatever. Yeah.
Yeah, it looks like a great tool.
Yeah.
Worth trying.
Of
definitely.
course. Okay, we have time. Mutation test is good, of course, but it has some problems. The first one is time, because every time I have a mutant for example, Bitcoin Core, I have to compile the code. It takes time. But I have to run the tests, and it takes time. Especially on Bitcoin Core, that we have functional tests that one functional test like takes more than 1 minute to run. So this is one of the issues we have on mutation testing because time. And another one is the equivalent mutant problem. It's basically when you mutate the code, but the behavior is the same, you know? So yeah, so of course your tests cannot detect that change because the behavior is the same. So this is the equivalent mutant problem. In another paper, what I did is basically running differential fuzzing between the mutant and the original code. So if I run it for hours and it doesn't crash, so I know that is an equivalent mutant. So I shouldn't care about it, you know? Yeah. There are other techniques like you can, there is the TCE, trivial compiler equivalence, when you compile the mutant and the source code and compare the binary, basically, because sometimes we do a mutation, but the compiler optimizes the code and basically are the same of the original one, so you can compare, but it detects only 20% of the equivalent mutants, basically. So I think the differential fuzzing is the most promising one I've seen, like, you know. Thank you.
Just one more question.
Yeah.
If the software, after mutating, passes the tests, could it also mean the presence of some dead code which not running at all, or it's running but not affecting anything?
Yes, yes. This is true. Also, for example, in Bitcoin Core, we have some cases where we have like if true, log. Of course, we don't test it, so I don't need to apply mutation on that if statement, you know. So, yeah. So my tool that I wrote for Bitcoin Core, basically it reads the AST of the code, and then it can see like, okay, this if statement only prints something, or it's a log debug, so I can skip mutating that part of the code to save resource, you know. So yeah, sometimes you mutate like that code, and it's not useful.
Thank you.
Any more questions, guys? So, I think it's it. Thank
Thank
you.
you.
Bruno.